335 years ago, a beam of light left a small, sun-like star in the constellation Reticulum. It traveled across a vacuum so vast that entire human civilizations rose and collapsed back on Earth while it was in transit. And just last year, that specific beam slipped past a planet the size of Saturn, picking up the fingerprint of a single molecule in its air. Finally, that light arrived at the gold-plated mirrors of the James Webb Space Telescope. That faint, ancient breath of light delivered the first concrete evidence of a room-temperature gas giant, breaking decades of scientific silence. For almost the entire history of exoplanet science, a gas giant meant one of two extremes. The first is a hot Jupiter, a planet orbiting so close to its star that its atmosphere is actively boiling off into space. The second extreme is the frozen giants of our own solar system, planets like Jupiter and Saturn, swinging slowly around a distant sun. This chart shows known planets plotted along a temperature scale. You can see clusters at the boiling and freezing edges, leaving a massive void in the center. TOI 199b drops directly into the dead center of that empty zone. It has a 105-day orbit and an equilibrium temperature of roughly 350 Kelvin, about the temperature of a warm oven. The problem with reading a temperate planet's air is the sheer physical difficulty of transmission spectroscopy. You are trying to read a tiny wisp of atmosphere against the blinding glare of a star, and on long orbits, transits are rare. Because the planet is temperate, its atmosphere is not puffed up by extreme heat, making the signal incredibly small. Its perfectly ordinary temperature is exactly why capturing this reading is a monumental achievement in astronomy. Researchers at the Jet Propulsion Laboratory pointed JWST at TOI 199b during a single transit, bypassing the old necessity of stacking years of observations to get a readable signal. The data returned an unambiguous signature of methane. This chart displays the light spectrum captured by the telescope. These sharp, specific vertical cuts represent methane. The data yields a base factor of 700, making it 700 times more likely to be a methane-bearing atmosphere. That is statistical certainty. But the flat, undisturbed sections of this same spectrum are equally strange. Standard formation models say a Saturn-class planet should be enriched with heavy elements, which would show up as clear carbon monoxide and carbon dioxide signatures right here. Notice that those expected signatures are completely missing. The planet's chemistry is surprisingly clean, lacking the buffet of heavy icy debris we expect giant planets to consume as they form. These missing molecules challenge current formation theories. They suggest this planet either bypassed the typical diet of icy debris or grew in a chemically depleted region of its stellar disk. While analyzing the data, researchers shifted their focus from the spectrum to the precise timing of when the planet crossed its star. The observed transits drifted. The planet's orbit had a subtle, irregular wobble, much like a metronome being gently nudged. That wobble is the gravitational tug of TOI 199c, a second hidden outer planet that is tilted out of our line of sight. Finding an unseen planet through gravity is a technique with a long history. In 1846, Urbain Le Verrier noticed a similar wobble in the orbit of Uranus. Without ever pointing a telescope, his mathematical predictions led directly to the discovery of Neptune. Gravity is honest in a way that light is not. This hidden tug reveals that TOI 199b belongs to a multi-planet system with its own unique architecture. For decades, chemical models predicted that in planetary atmospheres below 1000 Kelvin, carbon prefers to bond with hydrogen, meaning methane should dominate over carbon monoxide. Prior to TOI 199b, every temperate giant we knew about was too far or too dim to test this. The models were running entirely in the dark. At 350 Kelvin, TOI 199b perfectly matches the math. The methane appears exactly where the equations said it should be. This planet is a permanent baseline. It gives scientists a new ruler against which all future temperate gas giants will be measured. To be absolutely clear, TOI 199b is a gas giant. It has no solid surface and it is completely uninhabitable. But the researchers successfully read methane in a single transit, inferred an unseen companion through transit timing, and accurately modeled temperate chemistry. These are the exact techniques that are being sharpened right now for the future search for biosignatures on rocky, Earth-like planets. Successfully reading the air of a temperate Saturn across 300 light-years confirms that the search for life has moved from theoretical possibility to a project of technical refinement.